University, and I shall be talking to you about monads for the next hour or so. But before I start, I really have no idea with what kind of knowledge you're going into this talk. So I'd like to ask some questions. First of all, of the people in this room, who is actually here to listen to the talk? That is quite a significant percentage. All right. So who of you is comfortable with using the monad instance for maybe and kind of understands what it does and what it's supposed to do? That is also a significant percentage, although not quite as many. Okay, then I'll keep that part a bit shorter. How about the instance for lists? Let's see. The state monad? Great. Okay, then I'll redistribute some resources to the state monad. It's kind of tricky, to be honest. All right, then do notation. Most of you have probably used it at some point or the other, right? Hands up if you have. All right. Who of you would say that they completely understand what do notation does and could translate it into ordinary Haskell code? All right. Well, that's the sort of the structure. Okay, and then the monad laws. Who is familiar with them?
Hand raise.
Doing that by heart.
Good. Well, then basically what I'm going to do is I'm going to walk through these topics essentially in the order I just asked about them. So I'm going to talk about the monad instances for maybe, lists, state, and a little bit about I/O. And then I'm going to talk about do notation, what it does, and how it desugars into ordinary Haskell. And I'm going to talk very briefly about the monad laws. There's really not very much to say about them, but I'll say what I have to say. So, starting with maybe. I'll keep this short because most of you seem to be familiar with it. So as a reminder, the data type maybe is defined as either just a or nothing, and it's Haskell's replacement for null values, essentially. So if a maybe value is nothing, that means it is absent for whatever reason, and if it's just a value, then it means that the value is present and we can use it. And maybe is commonly used to signal error conditions of any kind. And as an example, we've here got, my example will be sort of like a web application, because everything is a web application these days. So we've got a user data type, and the user has a username defined right here. But since we're very privacy aware here at Google, we actually allow our users not to specify a name at all. So the username is maybe string. It might be absent if the user chooses not to specify a name for themselves. And then down here, we've got a super high performance web scale database for users, which is in this case a compile time function that maps IDs to users. In a real application, of course, you'd have some sort of database that you're querying, but for the purposes of this example, we've got a function that returns for the user, for the ID 1, myself, for the ID 2, Simon Peyton Jones, for the ID 3, Comic Sans, for the ID 4, a user, but that user has chosen not to give themselves a name. For the ID 5, a user who has chosen the empty name, and for any other ID, no user. So that's going to be the setup that we're working with. And the idea is that I'll try to motivate why we actually use the monad instance for maybe. So let's start with something relatively reasonable. We want the username for an ID. So we've got a function of type int to maybe username, and username is here represented as a string. All right. So conceptually, of course, what we'll do is we'll query the database. If the user is present, we'll try to get the username. If the user is not present, we'll return nothing right away because we can't return a username for the user that doesn't exist. So let's just implement this naively. We'll have to do case analysis on the result of our lookup query. And if that's nothing, we return nothing. If that's just something, we return the username. And of course, that username may also be non-existent, but we don't care if it's present. All right. Now, let's modify this function to do something slightly different, namely give us the first character of the username. So we'll define an auxiliary function, first character from string to maybe character, because of course for the empty string there is no first character. So first character of the empty string, aka the empty list, is nothing, and the first character of a list that is not empty is, well, the first character wrapped in a just constructor. So far so standard. And if we now turn to this function and turn it into first character for ID, which now returns a maybe car, then we'll have to again pattern match on whatever the username query returns. As a reminder, username is of course a regular function just defined using record syntax from user to maybe string. So if the username that we get is nothing, then we can't return the first character. If we get just a username, then we can return the first character of that username if it isn't empty. All right, let me quickly check if that actually all works, or if I mistyped something. No, it looks good, more or less. All right, and now if we get the first card for ID 1, that's me, that's J. We get the first card for ID 5, that's nothing, because user 5 is a user who has an empty username, and so on and so forth. Now what I'm getting at is that this is a really, really terrible way to write these sorts of functions, because essentially it doesn't scale at all. If you imagine now you don't have 3 functions that you want to apply one after the other, but like 5 functions or so, and they all take some input and return some maybe output, then chaining them in this manner is really ugly. And Haskell can do better, of course. So we'll define an operator. Actually, that's the wrong operator. We'll define this one, which is called the fish operator. Also occasionally called Kleisli composition, but fish is much better. And what we actually, essentially want to do is we want to chain functions of the form A to maybe B. So we'll take a first function from A to maybe B, a second function from B to maybe C, and what we get out of our operator is a function from A to maybe C. And you'll probably notice that this is very similar to composition, that's why it's called Kleisli composition, For composition, you'd have A to B, B to C, A to C. And here you've got a maybe for all the output or return values. So let's define that operator in general. Let's say we have a function f and a function g, and we'd like to compose them. So our result is obviously a function that receives a value of type A, which I'll denote by A. And what we can then do is, well, we can first apply the f to the A and receive a maybe B, and then we can do case analysis on that. And if it's nothing, we return nothing, because we can't chain the function g onto nothing. If it's just a value of type b, here represented by b, then we can apply the g function and we'll get a maybe c. So that's our composition operator. And now let's reformulate that first car for ID function in terms of that. Well, we first want to get the user. Then we want to get the username. And from the username, we want to get the first character. And those 6 lines can die. So that is quite handy, and primarily an example in how Haskell kills boilerplate code most of the time. What this has to do with monads is that this fish operator is a variant on the defining operator of monads, namely the bind operator. And so let's take a look at the monad type class. So this operator is called bind. And what it does is it takes a value of type MA, a function of type A to MB, and returns an MB. And you'll probably notice the similarity here. If you substitute maybe for M in this type signature, it's almost like this function here, only we drop the first component of the first function and of the last function. And I'll show later that the fish operator can actually be implemented in terms of the bind operator. But let's deal with that first. So the first interesting thing, and the first difficulty about the monad type class is that it is a so-called higher-kinded type class. And what this means is that down here you see that M is applied to another type. In this case, the type A, which may be some arbitrary type. So this means that in contrast to types like string or int, which cannot be applied to another type, if we substitute a string here, that wouldn't make too much sense because string A is not a thing that we can talk about. We need, for our monad type, a so-called type constructor, i.e. something that can be applied to one other type, and exactly one other type, in order to get a so-called concrete type. And concrete types are exactly those types which have values. So int is a concrete type, string is a concrete type. Maybe int is also a concrete type, because the maybe is fully applied. List of int would also be a concrete type, but list and maybe themselves are not concrete types because they need some other type in order to be able to have values. So that is the first difficulty, and that is why later we're going to write instance monad maybe and not instance monad maybe A. Because if you were to substitute maybe A for these M's here, you'd get a type that is, well, you apply maybe to 2 types, which it can't do. That was not the right key very much. All right. Back to the type operator now that we've cleared that up. So the bind operator is used to take a so-called action. This MA is called an action. What symbol? Tilde. And I'm going to call functions of type A to MB computation. Actually, I probably shouldn't use the tilde symbol here because it has a specific meaning in the Haskell context, which is not what I intend here. So let the triple equal sign mean I call it action and computation. Action is definitely standard nomenclature in the Haskell world. Computation, I'm not actually quite sure if that's my invention or if that is also standard parlance, but I'll assume that it is. So bind takes an action, feeds it to a computation in some to be specified manner, and returns another action. And then there is a second function that we'll be dealing with frequently, and that is return. It takes a value of type A and produces an action which has also the output type. And in order to make that less abstract, let's have a definition. And the monad instance for maybe works exactly as we've basically practiced all the way to this point. It takes an action, a maybe something, and feeds it to a computation if and only if the action is not nothing. If it is nothing, then we get a nothing back. If it is not nothing, then the next computation is executed and we get the result of that computation back. And so let us define a bind operator that does exactly that. If we've got an action, then we can pattern match on that action, or do case analysis on the action. If it's a nothing, we return nothing. If it's just something, we'll return the result of applying f to something. Oh, this is basically the pattern that I've been talking about all a day up to this point, so that should come as no surprise. And now the fish operator can relatively straightforwardly be expressed as exactly that, because if we apply f to a, then we get a maybe b, and we can just feed that into g using our new bind operator, and that simplifies the whole story quite considerably. Incidentally, the bind operator can also be defined using the fish operator, so these two are basically have the same power. Now the next thing that we need in order to close that chapter is return. And now for return we actually have two choices that would match up with the types. We could actually return nothing, because that is a legal value of type maybe A for any type A. And the reason why we don't do that will become clear when I talk about laws. But right now let me give you a very broad intuition. The idea of the maybe monad is error handling. So if you get an error along a chain of computations, you immediately drop the chain of computations and say, oi, I got an error on the way, I can't give you a result. And the idea behind return is always that it puts a normal value into a monadic context that is kind of most natural for the domain that we're working in. And we'll make this more formal later. There are laws as to what return can and cannot do. But right now, if we talk about errors, it would be relatively unnatural to take a value and map it to the computation that is always an error. Rather, it would be much more natural to map it to the computation that produces exactly that value and is successful in producing the value that we're talking about. So we'll actually, for the time being, go with just, representing the computation that produces just x. And of course, we can make that more point-free by removing the x on either side. So let me check. Wow, everything compiled, so it must be correct.
Sorry, but you were saying this last phrase to specify why return cannot return nothing? Or you had this idea about the return?
Well,
so just it's always would be just, right? You put in the context, it always has just
exactly.
One, but the maybe has also nothing.
Exactly. Yeah, so as I said, the types would match up with the just or nothing. So according to the type system, it wouldn't be a problem to return nothing here. It would be a violation of the monad laws. And I'm going to talk about that later. But right now, I can only really give you a very fuzzy idea of what return is supposed to do. And that idea is that it's supposed to put a value into a sort of neutral context.
But in case of, for example, either?
In case of either, you'd put it into the right context. I'm not going to talk about either specifically in this talk, but just as an aside, either is basically the same as maybe as far as the monad instance is concerned, because it is used for basically the same thing. It is also used for chaining computations which may produce errors, and the only difference is that with either you can specify which error has been produced, and so you can precisely locate the error if you so desire.
Sorry, but from this it follows that return implementation is coupled to the implementation of the bind.
It is.
That's what you mean by the law?
Yeah, exactly.
So if I change my return to, I don't know, some weird combination where it can return nothing, and then I have to change the bind as well.
Yeah, or the other way around, of course. If you change the bind, you may have to change the return. Yeah. At the end of the talk, I'll give the monad laws, and I'll probably also explain why or how they work out in the case of maybe. So I'll have to ask you to accept that until then.
No, it's good.
All right. So that is the part about maybe done. I believe this should have been nothing new for most of you, but it's a kind of primer for what is to come next. So any questions about that? No? That is good.
Sorry, one more.
Yes.
What happened with the terminal in the middle? Because for us it's slightly more convenient to look there. Got stuck on the floor.
Good question, to be honest.
There was some activity there, but it looks like something.
I think it just cut off.
Flipped, yeah.
Cut off.
It's split because it has the same content. Even the fish operator is updated to the latest version.
That's correct.
Yeah, it got cut off on the floor.
Some issue with the projector, I assume. Not my business. All right, so let us move on to lists. Lists are also monads in a very different way from how maybes are monads. But we can define a law-abiding monad instance for lists. And I'm just going to skip the formalities and proceed with the implementation and talk about why we do that a bit later. So for lists, our M in the signature of bind is the list type constructor represented by those angle brackets. And so if we substitute that into the type signature for bind, we get list of A, then a function from A to list of B, and we return a list of B's. And let me quickly give you the implementation because it's really short. Let me call it X's here, so that makes more sense. The implementation is this. done. And what this does is, in case you're not familiar with concat map, it basically just maps the a function f from A to a list of B over the list of A's, resulting in a list of B's. And then it concatenates those things in order to get f. It concatenates all of those lists together to get a single list of B's. So concat map is precisely concat composed with map. Or rather, concat map f is concat composed with map f. Otherwise, the types don't work. So that's the implementation. And the intuition behind the list monad is that it represents non-determinism. More precisely, the full exploration of non-determinism. So think of a list of A's as a non-deterministic value that may assume any value included in the list. And then think of a function A to list of B as a non-deterministic function that takes an argument of type A and produces any of the values included in the list that it produces. And so the idea behind the list monad is now chaining those computations together. And the way we chain them together is really quite natural for this kind of problem domain. We take the non-deterministic function, apply it to every potential value of the non-deterministic value, and we get a bunch of like more non-deterministic value of type B for a list of non-deterministic value for each input from the list of A's, and then we concatenate all those potential outputs together, and we get the list of outputs that may be produced by applying the non-deterministic function to the non-deterministic value. That's a lot of non-determinism. Yes?
If you follow this model, wouldn't it make sense that it also removes duplicates?
Pardon?
If you follow this model of thought, wouldn't it make sense that it should also remove duplicates from the resulting list?
It would, very much so. I believe that would be a violation of the monad laws, although I'm not 100% certain on that. It could be that you could do a similar thing with sets, but I'm not certain on that. We'd have to check. Actually, that would be quite a nice exercise. Maybe I'm going to do that after the talk. So, yeah, indeed, we may get duplicates if we follow this model. So it's sort of applicable in some circumstances. It's not a full-blown implementation of, for example, game tree search and so on and so forth. You can do basic tree searching, like for example, if you've got a game tree that is very conveniently modeled using the list monad, but it does have its limitations in the sense that as soon as you want to do anything but use those list functions, it becomes a bit awkward. But for now, let's proceed with the implementation. Well, this implementation is just the implementation of the general idea that I've just given. The idea that we take each input, apply the function f, collect all the results and concatenate them as a list of potential outputs. And now return is, again, a bit tricky to explain in such an informal way. But in this domain, it probably makes sense to think of a value of type x as a special case of a non-deterministic value, namely the non-deterministic value that can produce exactly one result and therefore isn't very non-deterministic at all. And in our model, this is represented by the singleton list that contains only x. That is a non-deterministic value that produces only one value. So let us talk about one little toy application. Unfortunately, I don't have the time to go into any great details about this, but let's look at just one small example. So we want a list of ints. And now what we can do is we can use a non-deterministic value that takes on the values 1 to 5, and we can chain that into a function. And probably the simplest function that we could chain it into would be if we just return the x. That's kind of written very redundantly, but such is the way. I'll change it later. And what this is going to do is recall that return x is equivalent to just the singleton list x. Well, it's going to warp all the inputs, replace every input by the singleton list that contains exactly that input, and concatenate the result together. So this is exactly equivalent to what we've passed in. And let me check if that's actually the case or if I've done something horribly wrong. No, good. All right. That's actually going to become important later because that is a general property of return. But I'll talk about that in the section about monad laws. Another thing that we could do is we could now use a properly non-deterministic function, namely the function that either produces the input times 2 or the input times 3. And if we use that, we get a list of potential outputs, and you'll see that the first two outputs belong to the 1, so they are 1 times 2 and 1 times 3 respectively, and so on for all the inputs. A slightly more interesting example, if we now take function and we use a second non-deterministic list, namely the list from 6 to 10. And we chain that into a different function. And we return a pair consisting of x and y. Well, what's going to happen here is the function first walks the first input and assigns x every potential value. And for every potential value of x, it executes the rest. And the rest is walking every potential value of y, i.e. 6 to 10, and then putting the x that we got before and the y into a pair. And what this does is it basically gives us all combinations of potential x's and potential y's. Let me demonstrate. No. All right. Type over here. Much better. Yeah. We got 1, 6, 1, 7, 1, 8, and 1, 9, 1, 10, 2, 6, 2, 7, 2, 8, 2, 9, 2, 10, and so on and so forth. And if you scale that example up, it becomes apparent why sometimes the list monad can actually reduce boilerplate by quite a lot. Because if you've got now, say, 5 lists and you want the combination of, or every potential combination of all of the values out of those lists, then you can simply use the list monad and write the whole thing with relative ease compared to what you would write in any other language if you were to write the combination of 5 lists manually. And of course, this also scales in the sense that you can add or remove lists at will, and the monad instance will take care of updating your combinations accordingly. So that is essentially why the list monad is very useful. Questions as to that instance? Yes?
In this particular example, do you actually need the full power of monads, or could you get by with applicative?
Yeah, that's an applicative example. You're right. It would be a monad example if I'd say x to 10 here. But yeah, right. I'm not going to talk about applicatives in this talk. They are basically a weaker version of monad that has more instances and is better optimizable in some cases. So it's relatively interesting, actually, applicatives, but I don't have the time to talk about them here. You should definitely read about them, though, if you haven't already. All right. On to something different then. The state monad. Now, states, most of you weren't particularly familiar with, and they are a bit tricky to get right. But the essential part is that we're going to talk about state transformations. And I'm going to call anything that has this form a function that takes a state and produces an output and a new state. I'm going to call that a state transformation. This doesn't have very much to do with the state monad transformer. That's a different concept that I'm not going to talk about in this talk. And of course it's related because we're talking about the state monad, and the state monad transformer is related to that. But a state transformation is hereby defined as a function with that particular signature, or that signature applied to some sort of type. So we're going to make state a monad, and we're going to do that because it would be quite useful to be able to chain these kinds of state transformations together. And the way we chain together is explicated, I think, quite nicely in the signature of bind. If you instantiate it with the type state s and remove the boilerplate that results from this new type wrapper. So conceptually, a state transformation is just a function. We wrap it into a new type in order to be able to make it an instance of monad without interfering with anything else. But conceptually, it helps to think of state transformations as just functions. So in that case, we get the following type. We get as a first input a state transformation from an input state, and that produces an output and a new state. We get as a second input a function that takes an input of type A, and we're going to get that from the first state transformation, of course. It takes a state, and we're going to use the new state that the first state transformation has produced for us, and we produce a B, an output of type B, and a new state. And the result will then be, well, the output of type B and the state after applying these two state transformations. And it's important to understand that we're always talking about functions here. So we're talking really just about the composition of functions of a particular kind in a particular way that enables us to think of these state transformations as, well, state transformations that chain like we would expect from stateful computations. If I chain a stateful computation to the next stateful computation, the idea is that, of course, the second stateful computation takes the state from the first and continues to work with it in whatever way it sees fit. So let us implement that. And I'm first going to do a mock implementation that assumes that this new type wrapper business up here doesn't exist. And then I'll move to the actual implementation because it's a lot of unnecessary, well, not unnecessary, but annoying wrapping and unwrapping of new type that just obscures the idea. So we have a state transformation, and we compose it with a function that includes another state transformation. And the result of our composition is supposed to be a function that takes an initial state. I should probably call it initial state, just to be clear. And what we then do is, well, we first apply the first state transformation. And what we get from that is we can deconstruct it into a pair consisting of an output of type A and a new state. And now we can apply the function f because we have a value of type A, which is quite handy in this case. We can apply that function to the value of type A and the new state. And what we get is a value of type B and yet another new state, and that's exactly what we wanted. So that is the implementation of this composition business. And now let me just silently do all the wrapping and unwrapping business. You'll see that the whole thing gets a lot more ugly, but such is the way of things. We have to wrap this into state, and then we actually have to pattern match here. And we get a new state transformation and can apply that to the new state. Okay. I changed nothing of actual value, so the thing is really still the same. All right. Now return. In this case, is also relatively straightforward, actually. If we want to make an arbitrary state computation that changes as little as possible about the context, well, then we make a state transformation that does nothing with the state, just ignores it, and passes it on to the next computation. So return in this sense is turning a stateless value into a stateless computation that is, a stateless computation in our framework for stateful computations, if you want to put it that way. That's probably not the clearest sentence people have ever said. So return is a stateful computation that takes a state and returns the x that we passed into it and leaves the state alone. Now, let us define a bunch of useful combinators on state, because they'll make working with this thing a whole lot more convenient. For instance, let us define get, a stateful computation in some state S that simply returns the state that we currently have. And this is relatively straightforward. We get a state.
Should it not have been an A if one of the S's out there at the time?
I'm using S because S stands for the type of the state, and get is the action that returns the current state.
Oh.
So that's why I'm choosing S. Of course, you could substitute for A or B or any other variable name
I was
you
just
like.
confused to see two S's, but I think I see what you mean, yeah.
Okay. So yeah, the implementation will actually make that super clear because we get the pair consisting of state as the output and state as the new state, meaning that this computation leaves the state alone. Sort of dual to that, not actually dual in any mathematical sense, but I'll have used that word here. Put is a computation that changes the state to whatever value we provide and returns no output. We might return the state as an output, but well, there's really no point to it, honestly. And put is defined like that in the standard libraries. So we'll use that form. So put called with a new state is a stateful computation that takes a state but ignores it completely because we're going to modify the state anyway. Then returns no value of any use and updates the state with the new state. The last common combinator, modify, takes a state modifying function and gives us again a stateful computation that modifies the state with the function we provided and otherwise does nothing. So it's a computation that takes the state, returns nothing meaningful, and applies f to the state. And these are really all the combinators you need in order to work with stateful computations. And let me give you a quick example. One area where Haskell is really inconvenient in comparison to impure languages is random numbers. Because in an impure language, you've basically got your global state, you've got your random number generator object, and you can query that at any time, if it's thread safe, also from any thread. And you get a new random number. And you can rely on that number being unique up to whatever your pseudo random number generator actually does inside it. So in Haskell, you can't really do that because you can't usually have mutable global state. And so what you have to do is you have to pass the random number generator around all the time. You pass it to a function, the function retrieves the next random number, updates the generator in the process, and you get back the new generator, which you then have to use for all your further computations, because if you use the old generator, it's a pure value, it's going to produce the exact same stream of random numbers that it would have produced before, which is relatively inconvenient for random number generators because the numbers end up not being very random. So this is one area where working with Haskell without the state monad is actually a pain, giant pain. But now with the state monad, we can do stuff like that. If, for example, we want a function that gets us a random element out of a list, then we define that function as taking a random number generator and producing an output of type A. And, or rather, an output of type maybe A if the index produced by the random number generator happens to be invalid for that particular list. And I'm not going to implement that right now. It's not particularly hard, but it's not particularly useful either. Rather, I'm going to demonstrate that you can then compose these functions really relatively effortlessly. For example, you can write test say we get a random element from a list of ints. Does that work with laziness? I don't know. Better not work with infinite lists. We get a random number from a from an input list, and then we can, for example, use that to get a random number from the input list of 1 up to the number we just drew. Or, for example, using some more monad combinators that I'm not going to discuss here in detail, but I recommend that you check out control.monad, the module, thoroughly. Lots of useful combinators in there, if you haven't seen already. Using those, we could, for example, make a list of lists. And we get the list 1 to 5. We get the list that contains 3. We get an empty list. And then we can just map a random element over that list, and it will give us back the list of random elements that were drawn from this input, from each of these lists in the input. And that is an example for the magic of monads, because note how we didn't have to pass around the state, namely the random number generator, by hand. This combinator basically does everything for us, because it executes for each of these lists the random element action, and by virtue of monadic composition, it takes the state that was updated by that computation, the next random number generator, passes it on to the next computation, produces the next result, and so on and so forth until the list is processed. And that is how you can compose stateful actions and thereby save yourself a lot of very tedious boilerplate code. So one piece is still missing from the puzzle of stateful computations, and that is how do you actually get something out of a stateful computation? Because recall that we're always talking about functions from a state to another state, and well, in the end we want to have the actual result rather than just a nice function. And the idea behind that is very simple, really. We just provide an initial state, then run our stateful computation and return the result. So if we've got our initial state, then we can unwrap the new type constructor, apply the st to the initial state, and take the first component, because in this case we're not interested in the final state. If you're interested in the final state, there are other combinators that can be used to get that. So this is how you deal with stateful computations in Haskell. And the last monad instance that I'm going to talk about very, very briefly is I/O, because I/O is actually the simplest of monads. And that will maybe come as a sort of surprise, because monad is deeply magical as well. It's basically built into Haskell. It's abstract, meaning you can't see the definition unless you look into the GHC source code, and so on and so forth. But the semantics of I/O are incredibly simple. The semantics are, firstly, if you chain two computations together, for example, say you do put string ln hello, and you chain that into a put string ln ZuriHac. And by the way, this is a variant of the bind operator that just ignores the result produced by the first action. If you chain those two computations together, you are guaranteed that firstly, both actions are actually executed. That is not the case for any monad. For example, if I chain put 5 into put 6, a sufficiently smart compiler could easily, well, it's not that easy, but could determine that the first computation is completely useless. Because it doesn't change the state, it doesn't produce a result that is used anywhere else, so it could be eliminated without any problems. In I/O, you don't have that. Every action gets executed. And the second thing is that every action gets executed precisely in the order that you specify them. So here the string hello is put before the string ZuriHac, which is very useful for I/O because we're dealing with side effects and those should usually be ordered. Of course, exceptions exist, for example, the fork I/O thingies that specify the computations are to be performed in parallel and so on and so forth. But the general idea of the I/O monad is that actions are executed sequentially. And those are really the two properties that define the monad implementation of I/O. Nothing more, nothing less. And to be honest, I don't have much else to say about it. At this point, you should be able to use the usual monad combinators and the combinators from control.monad to do basically whatever you want with I/O computations. So those are all the monad instances that I wanted to discuss. And now let's talk about laws. These are the monad laws. They are very, very simple. If you've seen a monoid before, which you probably all have, it's very similar to what a monoid does. And in fact, when people talk about how monads are monoids in the category of endofunctors, I believe the technical term is, then they mean, well, exactly this. We've got an identity element, it's returned, and we've got associativity, because the fish operator, Kleisli composition, associates. Those are the monad laws. And, well, there's really not too much else to say about them, unfortunately. They are incredibly simple, and they allow you to do some very basic refactoring that you're probably taking for granted anyway. For example, the associativity essentially specifies that the composition of 3 things doesn't depend on in which order these things are composed, which is really what you expect from any composition-like operator. If that weren't the case, it would be highly impractical. What's a bit more interesting is the identity property, and this is what I was going on about all the time with return. Here you've got your definition of what return can and cannot do. Namely, it must act as an identity for monadic composition. And in the case of maybe, if return were to return just simply nothing all the time, then this composition property would not hold. Because, well, if we throw nothing into any computation by the definition of the bind operator that is also used to define the fish operator, it'll just return nothing, regardless of what the computation would have liked to do. And if that were the case, well then we always get nothing here on the right-hand side, which would be in violation of the monad laws. And similar arguments apply to why we define return the way we define it in state and list and I/O and what have you. So those are the monad laws. And I'd like to make one more broader point. The simplicity of these monad laws combined with the rather diverse nature of the monads that we've seen in this talk. Non-determinism, error handling, stateful computations, effectful computations that change something about the computer. These are all vastly different things. And what I'd like to encourage you to do is stop trying, if you have been trying, to get a unified semantic interpretation of what monads are and what monads can do. Monads can do incredibly diverse things, and there is really no point in time where you can say, okay, now I understand what a monad is, so if you say my type is an instance of monad, I'll be able to write down the instance for you, no problem. That simply doesn't happen because every instance of the monad type class does relatively unique things that have very little to do with each other. And the only really the only element that that unifies these different instances are those three laws. But those three laws, they don't tell you very much at all. Only because something is an instance of the monad type, you can't say very much about what that instance is going to do. And so there is really no substitute to learning every monad instance in isolation, like we have been doing over the course of this talk. There are a lot of different other monad instances that are very interesting. The standard library has monads for a static environment, for example. It has monads for control flow, the continuation monad. It has monads for parsing in other libraries. It has monads for stateful I/O in a way, or streaming I/O. That's what I meant, not stateful. Streaming I/O. All of these things exist in our monads, but behave radically differently. And there is really no substitute to learning each of these instances one by one. So, one quick thing before I'm done. Oh wow, it is super late.
It's fine. We have 50 more minutes till the next talk, so officially you are done with your talk, but you can continue a bit.
I wasn't planning to bridge the whole gap into the next talk. Okay, so let me do that extremely quickly. As most of you are probably aware, do notation is a syntactic sugar for monadic notation. And these are essentially the transformation rules that apply. And you can picture do notation as a like recursive application of each of these transformation rules based on what the first statement of a do block is. And if the first statement is the assignment of a variable to the result of an action, then that means execute the action, bind its result to the variable x using the bind operator, and continue with whatever the other statements are. If your first action is an action whose result is not bound to any value, then you just execute the action, ignore its result, that's what the double and right arrow operator does, and continue with the other statements of the do block. If the do block consists of a single action, that's the termination case of the recursion, then just return whatever that action does. And then you can use some more like convenient syntactic sugar in do notation. You can use lets. The only caveat is that you don't write in here because reasons. And that is simply a pure binding of well, y to the variable x, and you continue with the rest of your statements. You can do case analysis, and this basically just chooses one action that you're going to execute next. Then it executes that action and continues with the rest of the statements of the do block. And pretty much the same thing applies to if you choose the next action, then continue with whatever else the do block contains. So that is do notation. The desugaring is really simple, and the intuition is also comparatively simple. Like executing an action, binding its result to a variable, probably not the most complex thing ever invented by man. Although it can be sometimes a bit intimidating for beginners because you have to watch out which of these are monadic values. The actions are always monadic, and the do block is always something in a monad. So a action of type MA, where M stands for any monad and A can be any type. But the X, the result that you get out of an action, is pure, is not a monadic thing. And so that can be a bit hard to work with for starters, but the concepts behind it are really not that hard. So that is the extent of my talk. That's what I wanted to say. If you've got any more questions, of course, please ask. If you've got questions that would fill the next 50 minutes, feel free to talk to me in private about them. Otherwise, I wish you happy hacking and have fun with the rest of the day.
Do you have some questions?
No question? Yes, I have a question.
So I can't remember the criticism is, but some people would argue that you shouldn't use the do notation, that it does more harm than good. Can you, if you know what I'm talking about, can you?
Yeah, I haven't read that wiki page in a while. I think the argument is basically that do notation, well, it's designed to look a bit imperative in nature. And that sometimes tricks beginners to think that it does things that it really doesn't. And it kind of encourages you to think in an imperative mindset and forget that do notation is really just syntactic sugar for purely functional computations. And in fact, most of the monads that we've looked about, actually all of them except I/O, are pure, referentially transparent, everything that you love about Haskell, even the state monad. And I think that is the basic criticism of do notation. I find do notation very convenient, as a matter of fact. And as soon as you grasp the concept, it becomes very much second nature and much easier to read, in my opinion, than just using the operators directly. It can be done. It's not terrible using the operators directly, but I find it harder to read. And I find the trade-off to be worth it. The trade-off being you have to teach beginners this new notation that may confuse a few of them. But yeah, of course, other opinions on that topic are well, just as valid as mine. By the way, one more thing, return really has nothing at all to do with imperative return statements. Like, not a thing. It's the biggest misnomer in all of Haskell, as far as I'm concerned. And it's a historical accident that's happened.
I think there is literally one common thing. They're often placed at the end of function. That's it. Nothing more.
All right.
Yes.
Yes, more questions.
So what does it mean that monad don't compose?
Well, I'd say the type class monad defines a way to compose computations. So did I say that they don't
No.
compose?
I just read somewhere that people prefer to use applicative because they compose and monad doesn't. Yeah.
It's usually set for the monad transformer thing when a transform stuff, not necessarily a monad. So.
Yeah, monad transformers are a different story, specifically the MTL variant of describing monad transformers. But yeah, I don't think I've heard that statement that monads don't compose.
I think what it usually means is if you have two different monads, like say reader and state, it's really hard to combine them. In fact, there's no standard way of combining the two.
But can you do that in general with applicatives?
Yes. So you can take any two applicative types, combine them automatically in a standard way, and get a new applicant.
Oh, that's handy. Okay. New knowledge was gained that day. I'll have to look into that. Oh, okay, then that is probably what people mean by that.
I don't know, maybe it's related to this, but when I'm in a do notation, basically I'm inside a monad, right?
Yeah, in a sense.
And I mean, one of the way I see it is that I extract the results from a computation, you know, and I pass it to the next one. What I would like to do is extracting values from different computation, from let's say from different monads. Is this possible in the do notation? Because I was doing something similar in Scala and I got problems. Let's say I don't know, I extract the value from a list, then from a maybe, and I want to combine them. The problem is that the do notation extracts from monad and then push it back to a monad, right?
Okay.
So the problem that I see is that in the case it is possible, in which monad the ending results would be pushed, and if it is not possible, why it is not?
So let me ensure that I know what you mean. You'd want to write something of the form x from function 1, y from function 2, and those are different monads.
Yeah.
And you like to compose those. No, that doesn't work in do notation, and the reason it doesn't work is actually, let's bring that up another time. Source 2. The desugaring for do notation, if you apply that to this do block, then you get function 1, and you bind the result, let's do the desugaring again, y, and bind the result, and then we actually don't do anything useful with it, so let's return the pair of x and y or something. That's unimportant. But the thing is that this desugaring basically already tells you that what you want to do is impossible, namely because function 1 should be composed by the definition of the bind operator with a computation that returns a result in the same monad. In the case of function 1, the monad would be maybe. However, function 2 is a computation in a different monad, namely either string, and so these two things cannot compose. What you can do, of course, is you can do
But let's say I have a list of int and I have a maybe of int, right? I want to multiply the content of maybe to each element of the list.
Okay.
So they are different more, but from, you know, it should be something doable. If the maybe is a just, I should be able to do this and then get out the results, a list of with all the value multiplied.
Yeah, the solution to that is you have to transform the one monad into the other. And the way you do that is you get your x out of the first function. Let's say you apply a function maybe to list. Does that actually work? Let's say we have a maybe value here for some list. Much better. Okay, now maybe to list turns your value into a list, and then of course you can compose two things. There's the y.
But there is no general approach because this is very specific, of course.
Yeah, there is indeed, I believe, no general approach, but I'm not qualified to comment on that.
I think for this specific case, you don't actually need monads at all. You can use applicative composition to do that. I think applicatives can do that for you.
In this specific case.
In this specific case.
But there's no general way.
But not for monads. Monads are too powerful. Monads can do too diverse things. There is no way to kind of define the rules in a consistent manner how they different monads compose. And since applicatives are much more restricted, you cannot. So in monads you can do like arbitrary graphs of computations, let's say, if you treat it as a graph. But in applicative, applicative is at most directed acyclic graph. So that's kind of the semantic difference between them. And with applicatives, since they are more restricted, you actually can deduce more about what they do. Hence, you can have a standard way to compose them. Monads are just too powerful, and there is no way. That's my understanding.
Are you both maybe instances of functor?
Yes, two. That's two.
So there's a monad in which both then are. You can always use that. So there's an instance functor which allows you to sort of do what you want to do, where there's an instance for both maybe and list, and you can use that. You can use that.
But of course you can't use
No.
I think functor is not powerful enough to do that.
But there are also instances of applicative.
Applicative is powerful enough. Functor is not powerful enough, and monad is too powerful.
And both these terms maybe are instances of applicative.
Yes, that's correct.
All right. So the monadic way to solve that problem would be this. You just basically convert the one thing or convert both things into the same monad and then use do notation as you would usually. Indeed, this is also a case where applicative would be sufficient and we don't need the part of monads. But let's not go into that detail.
Yeah. Actually, is it possible to approach this problem from the type class side? To create a type and then make it an instance of monad? So to compose the two types which he wanted, for example, maybe and list. To create another type and make it instance of monad to achieve this goal to have all this stuff in the do notation. Is it obvious what to do?
I don't think I'm quite sure what your idea is.
Like, so he wants to have different operations of different instances of a monad inside of one do block. Which you are saying is not possible because it always has to be one instance, right?
Well, you have to define one bind operator, essentially.
Yes, exactly.
If you find, like, if you make a type and make a lawful monad instance for that type that kind of composes your maybes and lists, I don't know if that's possible in general, but if it is possible, then yes, of course you can.
List can do everything that the maybe.
Yeah. Maybe is sort of like a list restricted to either the empty list constructor or the one element list constructor. Right. I see we should be finished right now, or we should be finished a while ago. Okay, then if any more questions arise, please do come see me and talk to me. Otherwise, have a nice day.